Hi, it's review time. Let's take a look at this AlienTek DP100 mini digital power supply. Supposedly it has 100-watt power output, 10 millivolts ripple. Of course, it's going to be switchable, and 30 volts, 5 amp adjustable capability. And apparently it's got gallium nitride charger in it, and it's got a Type C, it's got 4mm banana jacks on it, full load efficiency, 97%, and all the other specs. There you go, linked in down below. AlienTek didn't send this in. Thank you very much to the viewer who sent this in to the mailbag. So I decided to do a dedicated video because people love these low-cost products like this. Now, this is about, pricing's a bit hard, but it's about $60 US, but it's available cheaper than that, like $43 US or something, but it depends on like the accessories you want to get with it. Anyway, let's check it out and see what we get. I haven't looked at it yet, and there you go. You get a hard sell case with it. That's not too shabby. So, you know, if you want to take it on the road and whatnot, then that is going to protect it. So what do we get? We get no instrument. We get a USB, USB-A to USB-A. And then we get some alligator clips. Are they're like gold flashed. They're gold flashed. Look at them. Anyway, yeah, I'm sure it's the thinner stuff. And we've got a USB-C to DC converter. So, and we've got a little manual. So it must be in here. Yep, I can feel it. I can feel it. Oh, geez, that's tiny. That is... Nah, rip it open. Here you go. Ta-da! Look at that. That's pretty cute, isn't it? It is absolutely tiny. I do not have a big hand, but that is small. And if you want to see cute, of course, nothing is cuter than the micro supply here. But of course, you can't buy this. So yeah, portable USB power supplies. I've been doing those, but never sold it. Been doing it for like 15 years now. When I was a boy. Anyway, sorry, you can't buy it, but you can buy this thing. So let's peel that off. And DP100, so we probably have like a little OLED display. There you go. They do actually screw off and do have a tiny tot hole down in there in the banana jacks. But that's okay because they want to keep the form factor like really incredibly small. We've got a selection dial here. Right, so I've got USB-A there out so you can like charge stuff from it, I guess. Okay. Anyway, USB-C power input, and well, that's it. Let's power it up, shall we? I'll break my rule of turning it on before taking it apart, and oh, there you go. That's a nice boot. That is a small screen. Hang on, let me take the googles off here, and whoa, that's fuzzy. I can read it. But yeah, it's a small screen, but it's cute. There you go, volts, amps, watts, and we've got the input voltage, which is 12 volts, so it has negotiated the USB-C. I've just got it plugged into some external third-party plug pack here. It doesn't actually you can buy bundles with included chargers and things like that. So yeah, if you don't have one, VSET 1 volt there, and the ISET half an amp. And, oh, geez, I can barely read that even with my glasses, those little enunciators there. You can read this because you're viewing this on your big screen in your 4K resolution, you mongrels. But, yeah, even with my glasses on, I can barely see what those little enunciators do. So that's that's really annoying. Right, so without having read the manual, no RTFM, how do I switch it on? Our indicator does nothing. Okay, so what does that do? What does that do? Oh, look, they light up. They light up. Oh, pure wankery. Look at that. Oh, come on. I mean, really? Did you really need to do that? I mean, okay. But, oh, well, it tells you that it's on, I guess. It's an on indicator, right? And that's a switch to yellow there. So, okay. So that is your on-off. They should have labelled silkscreen on there, please. On-off. Like, come on. They've already gone to the effort to silkscreen. Doesn't cost you any more to silkscreen on top there. So, there you go. That was non-obvious, but there you go. 1 volt, and now we're live reading out. Let's short the sucker. Okay, basic short test. There you go. And, yeah, half an amp. No problems. So, and let's go all the way. Right, so how you set this is you press the stop button here, and the output is still live there. But you press that, and... there you go, your little tiny little cursor there shows up in purple, and once you're in there, then I can adjust it like that. So we can go up to 5 volts there. And yeah, Bob's your uncle. And that just switches between volts and amps set there. So we have gone live with 5 volts and now half an amp. So that interface is good enough. I don't mind that. Yeah, they just could have like added some silkscreen up there. But of course, you would get used to it pretty quick. I figured that out, no problems whatsoever. And then you can move along there and you can adjust in 10 millivolt increments. And then you can adjust in 1 milliamp increments there for your current adjust. We can go all the way with LBJ there. It does 3. No, it was 5 amps capability, right? There you go, 5 amps. Let's try it. I don't know if my plug pack can support this or not. But, yeah, well, there you go. It's giving me 5 amps output. But, of course, bugger all watts because the voltage has dropped right down because we have a complete short there. So, there you go. Up. It's cute. The user interface is good enough. I assume there's some sort of like this thing is not pushable, right? And that does nothing. So I like the fact that, you know, you can't accidentally just adjust that at all. You've got to actually physically put it into that mode. Does that actually time out? I hope so. Yep, it times out. There you go. Times out after like 5 seconds or something like that. Nice. So you can't accidentally adjust your voltage. That's what you want. Now for, yep, that was obvious if I held, oh, that's power. Okay. I thought that was going into the menu. No, that's your power button. See again. Silk screen, please. Like, how would you know? You wouldn't. And it defaults to power off. I wonder if you can change that. What if I hold down that and, okay, something else is coming up. Oh, I can't read that. That's lock. Okay, I literally had to get the magnifying glass out there to actually see this. And I've got my glasses on. Now, I can actually read that if I get, like, close to it, but oh geez, you know. Anyway, right, so that is a lock mode, okay? So that's excellent, okay? So we can just press that and go out of lock mode. What happens if we hold this down? See, there you go, and we got voltage set, over voltage protection, current set, and well, no, that's just like an info thing. That's a preset. Okay, so I was wondering if it had presets or not, but because it doesn't have dedicated preset buttons. Anyway, you can set your over current protection and your over voltage protection maximum. That'd probably just be software. That wouldn't be doing like a crowbar or anything like dedicated hardware for that, but that's common. And there you go. You can get 10 different presets. That's pretty good. Don't mind that at all. So what do you just... Oh, there you go. Right. Okay, so we can go in and adjust all the presets and the over voltage protection. So you can have separate over voltage protection and over current protection for each of the presets. That's very nice. I rather like this. Now, I see like 30.9 down there. I don't know what that is. I'm going to have an RTFM for that. But, of course, because it's only negotiated 12 volts here, from this particular charger that I'm using, that's all we're going to get. So we can only go to 11.7. So, yeah, you know, 300 millivolt drop is, or almost 400 millivolts drop there, is quite common for a pass element in a power supply like this. So that's why, you know, but you can go, you know, 400 millivolts up to the maximum voltage. That's pretty good. So it's negotiated 12 volts from the USB-C charger over here for whatever reason, the particular charger I'm using or whatever. But of course, the problem is that 12 volts is a common output voltage you might want on a power supply, but you can only go to 11.7 in that particular case. No fault of this, like, because, you know, it's not going to have like an internal boost converter to then bump that 12 volts up to 30. I mean, you're going to pay a price for this compact footprint like this, and that's all you expect from this thing. So yeah, that's fine. And here's the manual for those playing along at home. It's quite competently done. I like it. There's a quick start guide there. So what does that... Oh, device temperature. There you go. Okay, so that's displaying the temperature. What was it? 29 or something? Okay, fair enough. It's like 25 here in the lab at the moment. Celsius, that is. None of that Fahrenheit rubbish. Okay, and that USB-D down there indicator is the USB-A host output. So it looks like you can switch that off or on. So haven't figured out how to do that yet. Presumably it's not always on, which is good, I guess, because you don't want to take away from the capability. So operating instructions seems like a reasonably comprehensive little manual here seemed to have done a pretty good job. I don't mind it at all. Like anything that shows up red indicates abnormal working status, including over voltage protection, over current, over power protection, overheating protection, under voltage protection, reverse connection protection, and turn off the output. So it's pretty comprehensive. I like it. Aha, silly me. This is the adapter I've got. It's a 65 watt GAN USB thing. I was using USB-A. That's why I was only getting 12 volts. Let's try a USB-C cable. I think we'll negotiate a higher voltage. Oh, here we go. Big, thick as USB-C cable. Let's see what this sucker negotiates here. And 20 volts. There you go. No worries. So we should now be able to, how was it again? Go up like that. Should be able to, get about 19.5 volts there. Neat. So we do have 4 rubber baby buggy bumpers on the bottom that stop it sliding around. You know, if you get the cable hanging off, that's hanging off the bench there, and that's not pulling it off, so that's not too shabby. I had to read the manual to know to double click that to go into the menu there. So it claims it has 15 menu items. There you go, over voltage, over current protection. So that's global, is it? Whereas they have them individually for the presets. So that's pretty comprehensive. And rep is reverse polarity protection, so you can actually turn that off or on. So that's rather interesting, is it not? How do we change? Yep, do we change that? Nope. Yeah, we can change auto out to on. Yep, the manual says automatic output function upon startup. That's very nice. So yeah, they've like this has everything you want. Wow. And power delivery voltage, so you can actually, can you manually change that, can you? And it will 15 volts, 12 volts, okay, maybe that's like maximum it will negotiate or something? Anyway, of course you won't get to 30 volts. I think to get to our 30 volts, that's why they provide you with the lead. So we'll have to try that in a minute so that you can just feed an external power, 30 volt bench power supply right up its clacker, but if you have to do that, then kind of defeats the purpose of this, but 20 volts is plenty. Backlight set, volume set, USB mode is slave. So let's adjust that. Host, there you go. And I just switched on my micro supply here, which is being powered from here. So you can see that. There you go. So we can switch that off or on like that. Neat. And does that stay powered up when you... No, okay, let's try it. Let's power it up. Yep, that stays powered up. So it'll automatically come on, the USB output, and our output automatically switched on because we changed that setting. This is really nice. They really know what they're doing. They've thought about this. Theme control, white, so you can restore the theme. Version info, okay, so you can maybe you can update the firmware remotely in this thing. I have not looked, but yeah, I'm really quite happy with this. If you want another sense of the physical size of this thing, there it is compared to my micro supply there, and there it is compared to a tiny little Aneng multimeter there. So pretty groovy. Okay, let's crack this bad boy open. We've got 4 self-tappers on the bottom here. Hello, McFly. There we go. We're in. There you go. We've been mooned. That is is that the top side or the bottom side of the board? I'm not sure. Bloody black solder mask. Unbelievable. But that is going to be a double-sided load. But right off the bat, I'm liking how they've got the Loctite seal around the screws, which then go directly, they'd be machine screws, which go into the banana plugs there. So that's how they connect that. That's always a concern. How do they actually connect the banana plugs internally? That looks very good. Version 1.4 PCB. What I'll try and do is get, because of the black solder mask and everything else, I'll try and get a high-res photo of this and we'll go through it. Okay, we might have to take those out before we can get to the bottom side, so I've got to dig through that. And if we get the board out, that's what we got. Got a big metal can here. It looks like it's not soldered in, so I should be able to get that out. And there's a little board-to-board interconnect over here, which goes over to, and we'll have a squiz at that too, but we've got a little front panel. Is that like terminal sense or something? So I don't think it's, as I said, I don't think it's hardware over voltage protection. Anyway, there's our little display board. Once again, they've got the Loctite screws down here. It's all very nice. Okay, Like, this is like amazing value for money. Unbelievable. All right, let's have a close-up look at the PCB. As always, high-res photos available on EEVblog.com, and on the website you can also check out my merch as well in EEVblog.store. So here's the through-hole top side, and I have flipped and rotated this so that we have the positive output here, negative output down here, which matches the bottom side here and here. So sorry, all the electrons are going to fall out, but let's have a look. So obviously we've got USB-C power in here. This is our USB-A output, but we don't really care about that. All we care about is, well, basically this big section here, which is the buck converter, which converts the USB power delivery, however that's negotiated. And we'll take a quick look at how it does that, and then it down converts. So this is not like a SEPIC converter, which can buck and boost, which is why when we only fed in 12 volts, we couldn't get like the 30 volts output. You would need like a SEPIC or some other topology buck boost converter, basically, to actually do that. So this is only a buck converter. So you can only get, like, in this particular case, about 400 millivolts below whatever the USB power delivery has negotiated over here. And we've got one little MOSFET over here. In fact, all the MOSFETs in this are identical. So we'll take a look at the data sheet in a minute, but it's a 4040 N-channel type. So its position there looks like it's actually switching the power from the USB-C through to the rest of the buck converter. So essentially that's the on-off MOSFET there, because you saw we had a on-off soft power switch there. And these capacitors here, does it matter what brand they are? Of course they're going to be absolute rock bottom, because you're paying a rock bottom price. Anyway, these ones here look like solid jobbies, because you can't see the vents, which you'd typically have in there if they were wet electrolyte ones, but these are wet electrolyte, so Right, so we have our big ass inductor here, and we've got a large link over here, which could be a current shunt, but I don't think it is, because we'll see another current shunt on the bottom side, so maybe it's an optional thing. And up in this corner up here, this is actually our rotary shaft encoder for our little thumb wheel thing. And on our bottom side here, we've got the USB-C negotiation chip down here. We'll take a look at that. This is our main switching converter down here. We'll definitely take a look at that. These are our switching MOSFETs here. We've actually got two of them in parallel on the top, on the high side, and one on the bottom side here. We'll see that when we take a look at the data sheet here. We've got a couple of zero drift opamps here. They're the same. And basically our output here, it goes through here. That looks like a fuse, possibly. And then there's our big pins for our inductor there. And that's about all she wrote topology-wise. You know, there'll be a couple of other, you know, supervisory type stuff and amplifiers around here. And that's our main processor up here. And that one I haven't even looked at it, but that's probably the switching converter for the 5 volts output, which is here. And they've got another N-channel MOSFET over here, which switches the negative output. So that's how they're actually turning the output off or on. They're not actually switching the positive output, because as you can see, that just goes directly to the output of the switching inductor here. So they've actually put that on the low side, because maybe for a parts count thing, because they can reuse the same N-channel MOSFETs. You remember how I said they're all the same? And that other one on the top, all those are the same MOSFET, which is this a RU chips 4040 N-channel MOSFET here. 40 volts, 40 amps, more than capable for this sort of job. So they've used this N-channel MOSFET everywhere, so that lowers your BOM cost and also lowers your parts count in your pick and place machine. You don't need yet another reel of items. Reverse diode protection across the terminals here. Now, you're supposed to be able to switch that off or on, but I don't know how they're actually doing that. I mean, it's not this MOSFET. This MOSFET is definitely doing the output switching here. So I'm not sure what's doing there at all. And as you can see, there's nothing else on the top side here. They've got some output filter in, but that's about all she wrote. Now, I promised to show you this USB power delivery and how they do that. It's a CH224, and if we go to the videotape here, USB power delivery fast charging protocol sync controller. So this is interesting, and this is what you would use certainly in a product like this. So it does USB power delivery 3.0 and 2.0 and BC 1.2 negotiation as well, and it's capable of actually negotiating up to 100 watts power capability, which is the banner spec on the front of the thing. So supports 4 volts to 22 volts input, so it supports that 100 watts power delivery request, and used in power banks, chargers and all sorts of things. So let's actually go down and take a squiz here, and interestingly, it's got 3 configuration pins which you can digitally select for. You can actually request the voltage. So I believe that's how they're doing that manually in software. You remember how we saw that? You could actually manually select it. So the microcontroller is just driving those 3 configuration pins manually there to actually request a specific voltage. So all it does is just sits on the USB port here on the CC1 and CC2 pins here, and then that basically tells the charger side of it, the power delivery side of it, hey, I want, 20 volts please, give me that 100 watts capability. And if the charger goes, yeah, I can supply that, no worries, here you go. What everyone's really interested in is how do they do the constant current, constant voltage, power supply switching capability. Well, it's all done here in this 9928 jobby here, which is a buck converter. As I said, there's 2 N-channel MOSFETs there. They're in parallel because you can see all these 4 pins are shorted, all these 4 pins are shorted, and they're shorted to each other, and these 3 pins are shorted, these 3 pins are shorted and shorted to each other, and the 2 gate drives just buggering off there. So there's one on the low side, so that go down to ground, and this is going up to the positive side, and you can see we've got a current shunt resistor here. Looks like 8 milliohms, is it? And then they've just got the differential voltage going up there to the current sense pins on the 9928. So let's check out that jobby, because that is the heart and soul of this thing. It's an MP9928, and it's exactly what you'd choose for an application like this, because it's basically a single chip constant current, constant voltage switching power supply. But as I said, buck only, it won't boost up. So you've got to have the maximum capability. So 4 volts to 60 volts input voltage, dual N-channel MOSFET driver. Once again, that's a banner spec because it means that you can reduce your, not your parts count, but your part type count. So reduce your bill of materials. You can use the 1 N-channel MOSFET for both the high and low external MOSFET. You can see that here on the application circuit, we've got the high side, which is an N-channel, and the low side is an N-channel. So you don't need any P-channel. There's our big output inductor. That's the big wound jobby you saw on the top. There's our current sense resistor. That'd be that 8 milliohm jobby. And then you've got the 2 sense lines actually going back. So this actually supports full constant current capability built in. It's got it. You don't even need an external amplifier. Beauty. And it's got different current limiting modes here with iLimit and stuff. And it's pretty efficient. I think you can get up to like 96% efficiency at a couple of amps over here. Of course, at smaller currents, it's always going to drop. Your efficiency drops. But at smaller currents and smaller output power levels, you don't care. Block diagram for those playing along at home. There you go, times 12 current sense amplifier, fantastic. Once again, bill of materials reduction there, and you've got all your typical error amplifiers and everything for your regular, because it's got that regular voltage tapped feedback, but you can override that for setting the output voltage. And that iLimit pin we saw before, that just selects between different full-scale shunt voltages there. So you can trade off your shunt resistor value for resolution and that kind of stuff. And it's got thermal protection and all the other niceties. So yeah, it's the perfect chip for this application, no problems. And I told you there's a couple of zero drift op amps here. Let's take a look at those. They're a GS 8592. Haven't seen these before, but it's just some, cheap Asian brand that, you typically find in something like this. Zero drift, it's 0.01 microvolts per degree C for those playing along at home. And, seems quite reasonable. And it's certainly not like microcurrent level capabilities, 30 microvolts lower offset voltage, but you know, it's just a nice little cheap zero drift op amp. Wonder how much it costs. And the processor up here, it's we've seen this before in other Asian products like this. It's a 32-bit ARM Cortex jobby. It's an Artery AT32F415, meh, whatever, it's ARM. Now, as for this switcher up here, this 2420 or 34420, couldn't actually find any info on that. So I'm not sure what's doing there, but obviously it's a switcher, and well, you've got to have another switcher there for your USB-A output here. So it's got to be that. And as for this front panel connector, which has this 3-pin header here, this GEE couldn't get like an equivalent part for it, but obviously there are LEDs on the other side here. So there's one over here and there's one here on either side with those different colored LEDs. So this is basically a LED driver board. So that's got to be some sort of like little LED drivery thing, which you can remotely switch off or on via a interface here. But they seem to have gone to a fair bit of trouble for that, so, I don't know, hats off. But for the price point, you know, it's unbelievable. So you can see that they've got the plastic around here, so that's how it actually lights up. And they've obviously designed a custom pin interface here for the banana jacks. So that's about all she wrote in there, but there's actually a lot going on in this thing. So to get this down to the price point, it's really quite remarkable, actually. And of course, you can see the LCD, the OLED display or whatever it is up there. So yeah, it's just amazing that they can, you know, sell this thing for like as little as like $45 or something, you know, delivered. It's crazy. And in case you're wondering, no, this is not metal. This is actually a plastic case. And you can see the indentations for the MOSFETs here. They're the main switch-in MOSFETs, high and low side, and also something around here as well, those little SOT23. So thermal pads, I guess it's going to help a little bit, but this is not a metal back-in, so it's not like they're using that for power dissipation. It just kind of sort of helps. All right, feeding in external bench power supply here. I've got no output. It's just sitting there, no load at all. 31 volts maximum input. That's the max for this supply. So we're talking about 0.9 watts quiescent dissipation there. And that is, yeah, sure enough, that changes with voltage. If you lower the input voltage, it's going down and down, you know, half a watt, something like that. And the voltage display there actually does continuously update in real time. So once every second or something like that, they're actually updating that. So that's rather nice. And 31 volts input, we'll find that we're able to go all the way with LBJ right up to, you know, pretty close to that. So yeah, if you want your maximum output voltage, feed in the external DC supply. There ain't no boost in this baby. All right, let's measure the output noise here. I've got my scope probe properly connected up, times 10 mode. So the spec is less than 2 millivolts RMS and less than, well, I guess 10 millivolts max peak to peak. Now, of course, this will change depending on your source here, because there's only so much filtering you can put in this. So any noise that comes in from your external supply here, some of it is going to pass through here. So not all the noise we're going to see is going to be coming from the internal switcher, but we'll try different sources and see what happens. So in this particular case, I've got my linear bench supply over here. So 31 volts max input here. Okay, so we've got 5 volts output voltage here, 31 volts in from the linear bench supply. And let's take a look. So what we've got is AC RMS. I've done a whole video on that and why you're actually using it. It's actually standard deviation. I'll link that one in if you haven't seen it, and because it's important to be able to measure noise properly like this. So we can expand the time base there, and you can see that if I lower the intensity here like this, you can see that the higher frequency stuff is not as prominent. That's why you take AC RMS. It depends on how you want to measure noise there. But anyway, so if you're curious to know the switch-in frequency there, it's about 246 kilohertz or thereabouts. Oh, damn it. You know what happened? I forgot to put the shield back on the can. Oh, when I assembled it. Oh! I was going to say, that's me putting my hand on there is increasing that noise. Oh, God. Got to take it apart again. Oh, that's better. Well, there you have it. That's a bit different, isn't it? There you go. Once again, no load, external lab supply at 31 volts input, 5 volts output, and we're getting 450 microvolts AC RMS and 7.8. So we are under that 10 millivolts peak to peak. So let's ramp that load up again and see what's what. And switching over to the battery, external battery at 12 volts. Come on. AC coupling takes a while. There you go. That is like significantly cleaner coming from that external battery pack there. So yeah, once again, yeah, down and quite significantly, and see the waveform is quite substantially reduced as well. Now, just before I was using the USB-A output here, but now using the USB-C output, you can see it's changed again. So it really depends on that input source. Okay, so now I've got it connected up to my electronic load, so you can see that we're getting some extra noise because of the pickup of all the leads and everything. So I'm going to turn on a constant current load at 5 volts of 4.95 amps, so just under the 5 volt current supply, and wow, look at that. I'm powering it from the USB-C here, so let's go out there a little bit. Whoa, check that out. Jumping jackrabbit. Aha, no, look, it's flishy flashing. Look, something's flishy flashing down there. It's almost going into constant current mode. So the constant current mode is 5 amps, but we're too close to it. So something weird's happening there. Yeah, my input voltage is jumping all around the shop. The input, so that's dropping out. That's doing horrible stuff. So yeah, you've got to be careful of not only the supply that you're using, but also the cable as well. So let me plug in my bench supply and see if that makes a difference. Looking quite substantially better. No flickering. Yeah, okay, all good. So 28 volts input, 5 volts output. So we're delivering 22.3 watts there at 4, so it's dropped. So it's showing 5.01 volts out here. So I'm wondering if all that voltage drop is in my leads here, because I don't have a 4-wire terminal compensation on that at the moment. So let's actually measure the voltage on the terminals there. Yeah, there you go, 4.99. So that was just the drop in my leads over there. So the voltage regulation is excellent, and I'll just switch that off. So load off. There you go. That's actually really good. So actually, the voltage regulation is a lot better, because this is showing 4.998, and I thought the spec on this was pretty good, like 0.05 or something. But it's showing 4.98 there. So that's interesting. I'm going to go with the 786. Thank you very much. So that's our noise, just under 500 microvolts, AC RMS, 8.7 millivolts. I'm not going to bother turning on stats. So I'll switch the load on directly, and you can see not much difference. I mean, it changes a bit. There's some extra ripply stuff in there. If you turn down that, you can see the difference there. You can see the extra ripply stuff. So let's turn the intensity back up. But still, that's pretty good. That is 10 millivolts. So it meets the spec, 10 millivolts peak to peak, and it's well under the 2 millivolts AC RMS there. So very happy with that. But we're still within our 10 millivolt peak to peak noise there. Oh, well, basically on our spec there at 49 watts. So that's not too shabby. So let's increase let's go all the way. It's 14 volts, 15 volts. We're getting to the point where, no, my cable just dropped out there. So the cable I'm using just isn't good enough to do that. So 17 volts, yeah, it's barely enough. Yeah, no, whoa, something's smoking. Yeah, oh, the cables are smoking. Cables are smoking. Whoa, yeah. My wires are way too thin. Oh, the magic smoke. Magic smoke has escaped. Oh, goodness. Well, there's your I2R problem right there. They're little piddly pissant wires in there. Yeah, I need better than that. Oops. All right, after that embarrassing magic smoke incident, reason I use that dinky cable is because I couldn't find my adapter, which went out to 2 pins. I don't normally use like crocodile clip cables or something to go to. But anyway, I made up my own by 1.6 mil cable. That should do it into banana jacks. So yeah, that should hopefully do the business. And I think I've wired it the right way. Let's go. All right, now we're talking 4.9 amps, 73 watts output, taking about 76.7 watts from the power supply. So I don't know how much of that is lost in the cable and the connectors and everything else, and how much, because this is what's supposed to be 97% peak efficiency, sort of like peakish current there. So yeah, it's going to go reasonably cool. So at 73 watts output, we're talking 1.1 millivolts RMS, AC RMS, so we're still under the spec for that, and we're a bit over the peak-to-peak spec, but nah, it's neither here nor there. I'm not going to quibble over that for 73 watts output power, so that's pretty good. So let's bump that voltage up a bit more, shall we? 16 volts, 83, 88 watts, come on, 102 watts. Very nice. Oh, yeah, look at that. 15 millivolts, bit out of spec, who cares? Way under on the AC RMS, so that's really good. That is really quite capable, but of course, it all depends on your power source and the noise and your output capability and everything. Depends, but you can actually run it from a DC jack like that and get 100 watts out of the thing. I'm not feeling much in there. So, at 3%, maybe even 5% loss or something like that, you're only talking, 3-5 watts or something like that. So it should be able to handle that. So they don't need the metal case for the dissipation, because that's not too shabby at all. Okay, let's measure the turn on and off pulse response here. Got it going into a 2 ohm load. I've got 9 volts there. Okay, I've got it set up for single shot acquisition here. And let's give it a bell. Look at that. Wow. Clean as a whistle. Beautiful. Beautiful. No overshoot. And 20 milliseconds per division. 30 odd milliseconds for a startup. Beautiful. Okay, let's capture the switch off here. Negative slope trigger. Let's do single shot capture switching off. Boom. So I've got a bit of funny business going on there, but we're only talking like 5 microseconds, something like that. So probing or whatever. So I wouldn't worry about that at all. Switches off cleanly. And we'll capture the transition from constant voltage to constant current. Got constant voltage at the moment. That was out of constant current into constant voltage. So that's really clean. And as for voltage step response, yeah, that's pretty good. There we go. We've just got some steps there. That's pretty clean. As I was adjusting that, because where I was going down, so you expect it to curve with the output capacitance like that. So, yeah, that's nice. And what I've captured here is the switching from constant voltage into constant current mode. And you can see tiny little spike there, kind of like to be expected, I guess. But yeah, it's relatively clean, so not too bad. And then I captured going out of constant current mode back into constant voltage, and you can see that is where it happened there, and these were the extra just thumb wheel things I put in. So yeah, that's really clean. It's quite decent. So there you have it. That's the Alienware DP100, and I think that's a winning little unit. It's got a reasonable user interface. I think the screen is way too small on it, but then again, grumpy old person here complaining about the small screen. But ultimately, it is good enough for Australia, and considering that the size of this unit, you couldn't really do much better, I guess. But yeah, the user interface, could have done with some extra silk screening on there, but it works, and I'm quite happy with it. It's fully feature-packed, but I'm impressed with it, and like at any price really, but considering that you can get this for like, I don't know, 45, 50 bucks or something on special delivered. I think that includes delivery anyway. I like, it's just crazy. It's crazy good for a USB, like a small portable USB power supply. So it's worth having one of these, I think. So I'll put the link in down below. So thank you again to the viewer. Alienware didn't send this in. A viewer actually paid for this and sent it in because I guess they wanted me to review it. So yeah, it's really quite cool. Seems to meet all its specs. It's reasonably accurate, and it's got all the current and over voltage protections. Haven't really completely flogged the hell out of, but I could certainly get like 100 watts out of the thing, and I could get under the thermal camera and everything, but it doesn't seem to get hot even at like 100 watts output. So that's a really nice little unit. There's not really a feature that I thought, well, can you include this, please? It's got it all. So, yeah, I give that a big thumbs up. The DP100, that's rather remarkable. So, anyway, if you like that video, please give it a big thumbs up. And as always, you can discuss it down below and over on the EEVblog forum. High-res photos available on EEVblog.com if you're interested in that. As always, all my teardown photos go over there. I shoot with a separate camera, macro lens and everything. And leave comments on the video because I love the comments. Catch you next time.